chair is yours. And
yes, after presentation, I'm chair.
Yeah.
Okay, welcome to this session, and today we have in this session 5 presenter, and the first first and second presentation is invited presentation, and Dr. Evelina Slakeva, are you here? Dr. Evelina, can you hear me?
Hello.
Hello.
Hello. Yes, I'm available. Yes.
If you are ready, you can share your screen and you can start your presentation. Okay, okay, we can see your presentation, and
is it okay now?
Yes. Yes, okay.
Good. Then I will turn off my camera in order to have better quality, if you don't mind.
Okay.
So, ladies and gentlemen, it's my great pleasure to be here with you, although virtually. And first of all, I would like to express my sincere thanks to the organizers for inviting me to present this talk today. Of course, it's a pity that we couldn't meet in life as the previous congresses, but these are the unfortunate circumstances. And nevertheless, I believe that the Congress will keep its high standard and wonderful spirit. My talk today is about advanced alkaline water electrolysis. But first of all, let me say several words about the changing time we are living in. We not only have to change the way we communicate, we also change the way we work, and we change the attitude to the nature, to the future of the earth. And as far as the energy is concerned, we are in the period of very necessary transformation from carbon-based economy to hydrogen economy. This transformation is in the focus of the many of strategic documents of the countries all over the world. There are requirements for decrease of the emissions till 2050, nearly to zero, and the requirement to turn entirely to energy only based on renewable energy sources. In this transformation, the hydrogen will play a decisive key role. And therefore, we actually talk about hydrogen economy. What is the role of hydrogen? The previous speakers already said a lot about this element. It's a unique element, the smallest, the most abundant in the universe, but so difficult to be produced because it is not available in a free form on our planet. And when it is produced by steam reforming, there are a lot of CO2 and other emissions. As the previous speaker, now our chair, said, only 95%, nearly 95% of the hydrogen is produced by steam reforming. The only technology known which produces green hydrogen, meaning hydrogen produced by electrolysis of water, is the electrolysis. When the electrolysis uses electricity from renewable sources, we really have green hydrogen, which is clean, efficient, reliable, and independent. Actually, these are the main features of the future hydrogen economy. All people on the earth should have autonomous energy and use it when, where, and for what they need it. Sounds perfect, doesn't it? The green hydrogen cycle is illustrated on this slide, and you all are very well known for you. It's very well known for everybody, actually, not only for specialists nowadays. And the device which is in the focus of my talk is the hydrogen generator based on water electrolysis. This very, very simple, maybe one of the simplest electrochemical process at first glance. Water molecular, which splits to hydrogen and oxygen. Simple, isn't it? However, if you look in details, the partial electrode reactions have their peculiar features, and particularly the evolution of oxygen is complex because there are many, many steps through which this simple electrode reaction can pass with special mechanism. And in order to produce efficiently hydrogen and oxygen, we need special catalyst. Here, the brief history of electrolysis, discovered 1789. Then there was a long period during which the process was recognized as industrial method for hydrogen production. Then, about 50 years later, validated as technology for industrial purposes. And in 2018, it was declared as the cleanest method for storage of renewable energy. The hydrogen produced by this method can have a variety of applications. The previous lectures talked about them. As I said, we need a very efficient catalyst in order to make this simple process working properly. The thermodynamically, not a lot of energy is necessary, but the slow kinetic of the electrode reaction, particularly of the oxygen evolution reaction, increase the overvoltage and respectively the necessary energy. To make it efficient, we have to find materials which not only make the process faster, but also materials which are resistive to the oxidative conditions at the anode. And about the hydrogen reaction, well, it proceeds with low overvoltage. However, the most efficient catalyst is the platinum, which, as we all know, is expensive, and worse, it's not abundant on the earth. The classical alkaline water electrolysis, known for so many years and used industrially, has one disadvantage nowadays, which is important. This disadvantage is that the process needs constant energy. It is not very flexible toward the changes in the energy. And renewable energy sources, on the other hand, have not such reliable energy. They are changeable. And another important thing about the classical alkaline water electrolysis is that the liquid, the electrolyte, is very aggressive toward the environment. Therefore, for years, scientists work on development of electrolyzers using polymer electrolyte membrane, solid electrolyte, proton conductive. This technology nowadays is in very advanced stage of development, and such electrolyzer yield up to 20 normal cubic meter per hour. They already are available on the market, have high efficiency. The achieved current density is reaching 2 ampere per square centimeter at voltage around 2 volts. The produced hydrogen is very pure. They have a fast dynamic and startup and are compatible with the renewable energy sources. Sounds ideal again. However, nevertheless, all those wonderful features of PEM hydrogen generators, still the amount of hydrogen produced by this technology is not increasing very much. The most serious obstacle for this is the fact that the cost of this technology is still high. And the reason is that the used catalysts are noble metals, not only platinum, but also ruthenium and iridium, which are also not enough on the Earth. So there are more efforts in order to develop cheaper catalysts to make this technology widely used up nowadays. Having all this in mind, we decided to concentrate our efforts on the alkaline water electrolysis, but electrolysis which can change the liquid electrolyte with a polymer membrane in the way the proton conductive polymer membrane are used. The expectations are that such type of hydrogen generator will combine the advantages of the classical alkaline water electrolysis and PEM water electrolysis. This is the main element of such a water electrolyzer. In similarity to the proton conductive membrane, we have here OH conductive membrane, and cathode and anode are attached to this polymer, forming the well-known membrane electrode assembly. The transfer of electric charges is carried out by OH groups. The polymer electrolyte prevents the deposition of solid carbonaceous sediments at the electrolyte interface, which is a problem in the classical alkaline electrolysis cells. The used catalysts are inexpensive and available. These are mainly transition metals from the iron group. So the expectations are to combine these advantages with the high efficiency and compatibility with renewable energy sources typical for proton conductive membranes used in electrolysis. Here is illustrated the classical scheme for production of membrane electrode assemblies, which is applied in PEM water electrolyzers, and the same approach can be used for AEM electrolyzers. Synthesis of catalysts, usually in the form of powder, preparation of catalytic ink, and using different technologies, in our case, spraying, deposition of this catalytic ink on the gas diffusion layer, and then attaching the electrodes to the electrolyte membrane. It is well known that the main requirements toward catalysts are not only to be active, but also to have good stability, durability, and utilization. And using this type of spraying for attachment of catalyst on the gas diffusion layer, generally the utilization of the catalyst is around 40 to 50 maximum %. As I mentioned already, a problem with the electrode, with the materials for the anode electrode where oxygen evolution takes place, is the stability of the catalyst and the used catalytic supports. The catalytic support should have large specific surface area, good adhesion with the catalyst, and excellent electrical conductivity, plus should be chemically stable. Usually carbon black fibers, fullerenes, nanotubes are used. However, some of those materials suffer from oxidation and the high anodic potentials where the oxygen evolution takes place. Therefore, our efforts were focused on development of catalysts deposited on alternative catalytic supports. And besides replacing the traditionally used carbon-based catalytic support, we decided to use OH conductive polymer electrolyte membrane, which is laboratory prepared. And as a result, we have a membrane electrode assembly, which is cost efficient, stable during the water splitting. And we constructed our cell and then the stack of this electrolyzer using the zero gap concept for the alkaline water electrolysis, but replacing the separator membrane with electrolyte OH conductive membrane. And thus, the final objective is development of advanced alkaline green hydrogen generator. Our catalytic support is Magnelli-phase titanium oxide. Our first research activities on this material are with maybe 10 years old history already. And we use different type of Magnelli-phase titanium oxide. Here are shown the results from two types of this material. Ebonex of UK company Atraverde, which does not anymore perform and produce this material. And a second one, shortly named MPT, which has twice higher active developed surface. Using this support material, we prepared by a simple Zougel technique several types of catalysts, and today I will present the results based on platinum deposited on MPT, nickel deposited on MPT, and cobalt deposited on MPT. The Zougel method we applied uses acetylacetonate of metal, of those metals, and it needs preparation technique with temperature treatment not higher than 240 degrees Celsius, where the polymer, the organic material is evaporated. We prepared cobalt with different percent weight ratio between the cobalt and support, starting from 20 and reaching 100% cobalt without any support. And the same we did for nickel. We performed the usual characterization technique to see what is the distribution, what is the reproducibility of the method, what type of cobalt and nickel we have deposited. Generally, I would say, and not to go into details, that the method is very well reproducible, and the size of the metal nanoparticles produced by this method is around in the range between 25 to 40 nanometers, depending on the weight percentage of the metal. Here are shown the same results for nickel. Nickel particles are a bit smaller than cobalt ones. And on the next slide, you see the electrochemical characterization of the activity of this catalyst toward oxygen evolution reaction on the left side up and hydrogen evolution reaction on the right side up. We discovered a very interesting feature. The maximum activity for the oxygen evolution we obtained for cobalt with 30% cobalt in the mixed cobalt NPT catalyst. For nickel, this percentage was 40. The more metal we applied, the lower was the activity. And when we compared the results of pure metals with catalysts with maximum activity, cobalt 30 and nickel 40, accordingly on the left and right side, you can see that the used material for support, this Magnelli phase titania, not only plays the role of catalytic support, but also participates in the increase of the catalytic activity. That means that there is electronic interaction between support and the catalytic metal, known as metal acid interactive effect. This is well-known effect, and in our case it's very clearly distinguished.
Dr. Evelina, you have 5 minutes.
Thank you. So the next thing I would like to show is the membrane we have used. This membrane is based on benzimidazole, p-parabenzimidazole, but we have put in it a filament of montmorillonite. This is an inorganic material which has a double-layered structure, and the effect of its addition is increase of mechanical stability. And this membrane is doped with potassium hydroxide at laboratory conditions. Thus, its OH conductivity was increased remarkably. We published a paper about this. It's 1,400 millisiemens per centimeter, which is a very, very good conductivity. Then we prepared 5 types of membrane electrode assembly to compare the properties both of the membrane in comparison with the commercial one. Membrane 1, platinum electrodes for anode and cathode, and the commercial membrane. Membrane electrode assembly 2, the same electrodes but with the laboratory made membrane. Then we replace cathode with nickel, anode with cobalt, compared the properties of this membrane with the pure platinum membrane, and finally we prepared the membrane electrode assembly on the cathode with our nickel supported on MPT, on the anode with cobalt supported on NMT, and using our laboratory made membrane. We use very low catalytic loading of 0.5 milligram per square centimeter, not to use a big amount of platinum. And firstly, we made our screening procedure in a small laboratory electrolysis cell with 1 square centimeter working area of membrane electrode assembly. And here are the results showing the comparison in regard to the properties of the membrane. As you can see, the red curve, which represent the results for the membrane electrode assembly with the laboratory membrane, we have a much lower over voltages for both electrode reactions using the laboratory membrane. And the only explanation for this is the higher electric conductivity. There are no other reasons to have such a difference in the performance of both MEA. On the next slide, left side, you can see comparison of the hydrogen evolution reaction on membrane electrode assembly with platinum cathode and with nickel supported on MPT cathode. On the right side, the same, but about the anodic reaction of the oxygen evolution. Clearly, we have improvement of the performance using our catalyst compared to the platinum electrodes. And this was very encouraging fact. Therefore, we scaled up our electrode and used laboratory electrolysis cell with a much higher surface area, 12 square centimeters, and made a temperature test to see how it performs. At 60 degrees, we have the best performance. At higher, there was a not so stable behavior. And finally, we made a stack of 12 such membrane electrode assembly. We achieve a very stable performance of the stack with identical behavior of each cell in the stack, and efficiency at the 2-volt cell voltage of 52%. Also, we perform some dynamic tests, the so-called accelerated test, in order to see how in the long term this hydrogen generator will perform. And up to now, we can say that the results are extremely optimistic because we have not increased the catalytic loading yet. We have not did some tuning of the design of our stack. So there are a lot of approaches we already consider how to improve even further the performance of this, I would say, very cost-efficient device. To conclude, just shortly, would say that Magnelli phase titanium oxide has a very good potential to replace carbon materials for supports in water electrolysis, that newly synthesized non-noble catalysts demonstrate improved performance with high current density and better cost efficiency compared to platinum. The design of the electrolysis cell with anion exchange membrane ensure reliable and reproducible long-term operation, both in stationary and in dynamic accelerated test, and further scaling of production capacity is in progress. So maybe next year in Istanbul, we can report the development of this research further. And I'd like to thank you for your attention. Here the
thank you,
thanks
Dr.
to the financing organization and my team. Thank you very much.
Thank you for your nice presentation. Dear participant, if you have any question, you can write from the chat. I will ask the Dr. Evelina. Okay. Okay, thank you again, Dr. Evelina, for your nice presentation.
Thank you as well.
Bye. The next invited speaker is Dr. Erol Kurt from Gazi University, and the presentation title is The Role of the Hydrogen Energy in an Energized World. Erol Bey, Dr. Erol Bey,
Yes.
are you here?
I
Can't, okay, I see. If you are ready, you can share your presentation.
Yes. Please confirm if it is seen.
Yes, I can see.
It is okay, yeah?
Okay.
Mhm. Okay. So, first of all, I would like to thank to
Please, pardon, please pass the presentation mode.
presentation mode, okay? Just wait a bit.
Please press F5.
Yeah, I am making it, but it doesn't accept. I don't know why. It still doesn't work. I don't know. Let's see. I will try to do it from the part. Is it okay?
Yes.
Okay.
Very good. Very good. I'm happy to hear that. Okay. First of all, thank you very much to prepare such a good conference media here. I would like to thank to all the organizers here, and I would like to give a broad hydrogen energy perspective today for the audience, and I will give some question marks, of course, for the brains of academicians. My talk will be about the role of hydrogen energy in the energized world. Thank you very much. So I will start with a small abstract which gives some identities about the work, and then I will go into details. Energy density of liquid hydrogen is about 9.3 megajoule per liter. So this is the lowest one compared to other oil and fossil fuels. But in our modern world, hydrogen is mostly used to find a place for many applications, including transportation sector, household usage, and industrial, and especially industrial and chemistry related ones, which I will point out later on, especially for ammonia production and so on. So the fuel cell stacks can have various power scales depending upon the power of vehicle engines, and strictly speaking, most of the vehicles can operate with a fuel cell power between 30 kilowatts to the 200 kilowatts. For the household applications, mainly the electrolysis and DC-DC converter systems are used to produce the gas, considering an average house requiring 1 kilowatt power. Hence, it makes 2.93 kilowatt hour daily consumption energy. The produced hydrogen can be used in fuel cells or for any other applications, including combustion scheme, and also because of the photoconversion, electrochemistry process techniques are still unstable, but we will not go into details. So some other speakers have already talked about it. It's also obvious from the trend that the installed power of hydrogen energy electrolysis market increases worldwide beyond 50 megawatts. And in many developed countries, a hydrogen blending process also exists for the natural gas grids. Some of them, they use the mixed ones, and especially for the combustion cases. And also hydrogen mixed systems assist to decrease the carbon release to the environment, which I will point out later on. So the contents of my talk is that, but I will skip some of the slides because the time is not so long to shed a light on all those topics. But I'm, as I said, I am trying to give some small information about the worldwide stage of the hydrogen production and all other sectors. So this is a very interesting figure. Let's look at this. You will see here at the right side the population of our world, and then in the left hand side you see the annual production in gigatons of oil equivalents. So please keep in mind. And the interesting point is that you see from 2050s, no, 2020, sorry, 2020 on, the population starts to decrease. So this is an estimation. So my first question mark comes from this plot. According to Jan Lahiri from 2006 paper, this is a scientific paper, we see that there is a population decrease in the world. So, so this can be caused about COVID-like, ill scans or any other war planes, or I don't know. It is not scientific. I cannot go into details, but I see lots of this kind of estimation plots all over the world, which are made from different authors. So please keep in mind that COVID-like pandemic cases or maybe any other population reduced releasing scans can come in maybe 50 or 100 years later on after this case. And you will also see that depending on the decrease in population, but I would say that I do not believe in this population decrease. I mean, to be honest, for my individual idea, the authors think that the coal, oil, gas, and other energy-related production should be decreased. So this is mainly there should be a decrease of traditional cases, which is we call fossil energy. We say fossil sources. So we have to somehow replace them with the renewable cases. So this is my first question mark, if it is realistic, I mean this population decrease or not. So, okay, what is the motivation on making such a kind of hydrogen energy wide screen of the world? Hydrogen and fuel cells have suffered a lost decade after high expectations in 2000 failed to materialize. And the second one, three factors are enabling the sector to regain momentum, because we see that the momentum is still not available when we compare with photovoltaic systems and also winds. So I will show later on that there exists a very interesting difference between the growth of hydrogen energy sector and also wind and photovoltaic. So the first thing that we can mention about that, the improvements in technology and manufacturing mean that the cost about $60,000 in 2005, but now it decreased for the hydrogen technology, I mean $10,000. So when we see the pilots, you will see that the prices going down, but that's really good for the renewable hydrogen systems. And you also see a minus 26% decrease on the also including the carbon capturing. This is CCS means carbon captured systems, which are used mainly in the industry, I mean factories. So you see that these euros per kilogram produced is also decreased when we talk about the evolution of the production cost. So that's very good for the hydrogen energy systems. At least we can, it is promoting, I mean. So the commercial products are becoming widely available, and significant uptake is occurring in specific sectors. Also, for my third point is that a strengthened global resolve to mitigate climate change is coupled with increasing realization that clean power alone is insufficient due to the complexity of decarbonizing heat and transport. So here you see there is a scheme of hydrogen production from the left upper part of the figure. You have from wind, coal. Of course, we do not prefer coal, but in many countries, we have at the first stage, in order to produce the energy, we need it because this is the planning action for the first step. We need some case of coal, wind and solar energy. We produce the electricity from that, and then from the water, we use the electrolysis methods, and we get the hydrogen to the storage systems. And then we can make it two different scenarios to deliver it. First, we can put it into the ammonia for the agricultural products, and also this product can go to the destination with ships, special ships, and also we can directly confirm it to the grid services, and using the supply and distribution system. For instance, they use Australia, but overseas countries, you have a chance to give this kind of supply distribution too. Okay, so after this production scheme, we can skip to natural gas networking. And in that case, there are some applications worldwide to mix some hydrogen products into the natural gas systems and any other combustion related applications. Mainly, these are used for the industrial cases for heating, and also production of electricity, and also for the residential applications. So here, heating and electrical power generation, and also nowadays it is very hot topic. So therefore, I always say my students, PhD students and master students, to go into the electrical vehicle car supply systems. Here you see the fuel cell vehicles, and in Europe and many modern countries, there are lots of fuel cell vehicle systems. So that's a very good idea to improve also the hydrogen energy sector. And also, as you see at the last left part, industrial applications exist. So mainly, I do not go into details, but you see that for the household applications, especially, you need a converter system, and the sunlight comes, and then from that, with the photovoltaic systems, you can get the electrolyzer active, and then you can produce hydrogen and store it, and then you can use it for fuel cell for the electricity supply. So there can be a question about that. If we have electricity from photovoltaics, why do we have hydrogen again to produce electricity? Because at the night time we do not have sun, so we do not have sunlight. Yes, some of them can argue that we have battery. Yes, but batteries are not so efficient, as I will talk you. So therefore, hydrogen storage can be much more good solution for household applications also, as in industrial applications. Okay. When we look at the global greenhouse gas emissions, especially 2014, but it does not change too much. Um, let's look at the shared emission by the source. Uh, at the left-hand side, you will see that 48 or 49% total emissions per year exist, and from these, electricity and heat is the yellow one, the blue one is industrial, so the most of the emission comes from the industry, as we expect, and from the transport sector also we have the contribution, and with the red one and also the yellow one, agriculture and land use, there exists emissions. So in the agenda of the world now, countries in the world, this is the leading task to decrease the emission, carbonization from the, especially the traditional ones, and skip the energy sector more and more to the renewable case. So therefore, for instance, the rate of electricity production with emissions falls to 25%, and also compared to 68% over the coming 15 years, we have this value. And also solutions needed to make transport and buildings sustainable, that are cost effective and appealing to consumers. And also hydrogen and fuel cell technologies, which, because we have to divide them in many sources, they use hydrogen together with fuel cell. No, this is not correct, not correct approach. Hydrogen is different and fuel cell technology is different. But of course, you can use two of them together to have the work. So that's another point. Okay, when we look at the global hydrogen consumption by the industry, as you will see, there exists a petroleum refining system, 25%, and also methanol production for agriculture, 10% mostly, and ammonia production, that's especially for agriculture, but methanol is, methanol is for the chemistry and all other industrial production we need. And for the transport section, 10,000 comes for the consumption. So if we are wishing to have a hydrogen revolution, especially compare the hydrogen production with the wind and solar energy, we have to follow the rule of consumption. So especially we see that ammonia production, I mean for the agricultural cases especially, is a very good industry. So therefore, Turkey is a agricultural country, so we can have, or we can find a way to make ammonia production as a leading sector in our country, in this case, in order to have much more strong budget to compete with other countries in this scale. Of course, also, as I will mention about the transmission and transport sector, we need hydrogen energy applications also. And here, for instance, standard Chinese household in rural and urban areas, you see some household energy consume rates here. So mainly this kind of, I do not go into details, but the idea is that mainly this consumption scales of energy can be provided by PV hydrogen like systems in order to have a more sustainable future. Okay, 13 international corporations recently formed the Hydrogen Council in the UN, United Nations Assembly. So to position hydrogen among the key solutions of the energy transition, can be made as follows. Hydrogen can be produced from many feedstocks and processes with varying greenhouse gas and other emissions, costs and infrastructural requirements. Secondly, hydrogen can be used in many ways, including without fuel cells. Fuel cells can operate using fuels other than hydrogen, as I have pointed out a few slides before. Third, hydrogen and fuel cells can contribute in many ways, spanning the entire energy system, and hydrogen infrastructure may be costly, but pathways include several low-cost incremental routes. So, for instance, we can have a good example. 2017, UK's Hydrogen and Fuel Cell Supergun Hub published a white paper systematically assessing the current status and future prospects of hydrogen and fuel cells in future energy systems. Okay, I do not go into details about transportation, but I will just give some slides because it's very long. You see here in this pie chart, heavy trucks, light trucks, marine and other transport systems, and also air, air transport systems, bus especially, and also private cars and motorbikes. There exist, you will see that for the hydrogen and fuel cell systems, cars and motorbikes really gets the 45%, very huge percentage, and also passengers, you see 63% passengers exist, and from the road and non-road cases, we see about the usage of the hydrogen, we have 71% road and 29% non-road cases when we look at the worldwide trajectory. Okay, here in this plot, we give some battery stacks. I mean, this is PBA battery and nickel battery and lithium-ion batteries. And at the right-hand side, you see fuel cell hydrogen tanks. And this is the range, which is taken by the energy, and it goes to the, for instance, 400 miles with a tank. But the point is that energy storage system volume is important, because the energy storage volume is small about the fuel cell and hydrogen tanks. But when we compare with the batteries, you see that the battery system volumes much more higher, maybe 2 times, sometimes 3 times, and 4 times if you use PBA battery systems. So that's very, very good actually for the hydrogen energy part to use this feature and characteristics of fuel cell and hydrogen tanks in order to have much more elongated transport. So therefore, in Europe and many modern countries, including Japan and also America, they use the hydrogen system and fuel cell system for the transport sectors. And you also see that the emissions have increased also for the share of renewable energy in UK transport. And we also see that hydrogen represents one of 3 main options for low carbon transport alongside biofuels and electric vehicles.
Dr. Kurt, you have 3 minutes.
Yes. Okay. So you also see here the specific energy between the batteries and also tank systems, hydrogen energy systems. I skip. In many countries now, powertrains are driven by hydrogen, and in private cars, you will see 45% we have hydrogen cars in many European countries, and also in Turkey. We should improve this fuel cell and hydrogen part of energy transportation. And also there are different cases about infrastructure, ranges, lifetime, and so on. These are the superiorities of hydrogen energy systems, passenger cars also for diesel and non-diesel ones. There are many different combustion applications about hydrogen, but you see in Turkey there is not too much notifying place for the refueling stations of hydrogen. So this map should be changed. In Turkey, we should more promote about hydrogen sector in order to have much more carbon-free future. And also Horizon projects are good ideas to do it. And I skipped all these transport sector. It is including ships and Europlanes, also forklifts and industrial. And also from the heat and industry, we have lots of um, uh, usable areas, for instance, for natural gas and convert the electricity and so on. For instance, here you see the UK case and many other countries, including Norway case, for the heating and electricity production. There are some coal and gas and biomass and electricity, especially for China and India. Biomass plays an important role. For the future decarbonization option for the heat, there are different views. So I do not go into details, but from the slides you can get much more detailed information. And also share of housing stock, you see that the gas is getting much more important share for the future technologies. And there are different hydrogen fuel cell system. You will see, especially from the literature, that proton exchange membrane systems, solid oxides, phosphoric acid and molten carbonate systems, they all have different characteristics about the installation cost and cumulative capacity. So especially the phosphoric acid and molten carbonate systems, fuel cells, are mainly used in industrial bodies. So I do not go into details about the thermal capacity and so on. These are already in the literature. Mainly the electricity from the gas, 11%, 8% oil, and traditional from 33%, and 48% electricity comes from coal, oil, and gas for the carbon emission of the world. Okay, this is somehow similar plot which I have shown before. For the global power systems,
Dr. Kurt, you exit your time.
Okay. Just
you don't have any time.
Okay. So
okay.
We have some slides. So I would say, as the last word, a hydrogen revolution is required in order to get this dot into the upper part when we compare with wind and solar system. Thank you very much. And yeah, I am ready for questions. And we also have some conference in November.
Thank you, Dr. Kurt, for your nice presentation. Dear participants, if you have any question, you can write from chat, and I will ask to Dr. Kurt. Okay, you don't have any question, Dr. Kurt. Thank you again.
Thank you very much.
Okay. Now, the third speaker is Hüseyin Gürbüz, Dr. Hüseyin Gürbüz. The presentation title is the performance analysis of the electric vehicle powered by hydrogen PEM fuel cell in different driving cycles. Dr. Gürbüz, okay, if you are ready, please share. Yes, we can see. Okay, if you are ready, you can start. You have 15 minutes, okay?
Okay. Thank you, Ms. Professor Dr. Yusel Devrim. My presentation title, Performance Analysis of Electric Vehicle Powered by Hydrogen PEM Fuel Cell in Different Driving Cycles. Electric vehicle make a very important contribution to eliminating emissions from being a threat to human and environmental health, because approximately 55% of the world's total energy consumption originates from the transportation sector powered by fossil fuel. In addition, fuel cell electric vehicle can be reduce harmful emissions by 99.2% as they don't consume conventional fuel. However, huge batteries are used in electric vehicle. Also, in addition to environmental damage of materials such as lithium, cobalt, and nickel used in batteries, the performance of electric vehicle is negatively affected due to the short range of the vehicles, high charging infrastructure cost, and high electric generation cost. Fuel cell electric vehicle eliminate these concerns because the hydrogen fuel cell provides clean energy and provides easy and fast refueling like conventional vehicles. In addition, hydrogen supply in PEM fuel cell can be performance in less than 10 minutes. Today, there are 5 million electric vehicles worldwide. The number of electric vehicles is predicted to reach 50 million units worldwide by the 2030. With the participation of new and powerful candidates such as Turkey, the number of electric vehicles is expected to reach 12 million in a short time. However, electric vehicle must provide the comfort of conventional vehicles, especially in terms of range. Therefore, some analyses should be made on fuel cell electric vehicles. In this study, energy consumption analysis of the PEM fuel cell and battery in FTP57 need and 12 driving cycle of the fuel cell electric vehicle were performed in G2 suite simulation so far. PEM fuel cell, proton electrode membrane fuel cell, generates electrical energy by using the chemical energy of hydrogen gas. The PEM fuel cell shown in figure can be used as the continuous source of electricity in the battery electric vehicle. When we examine the fuel cell elements, there is a single PEM fuel cell can ascend simply in the picture. Between those plates, red plates, are coated an anode electrode and bipolar flow plates. In the middle of the fuel cell is a selective permeable proton electrode membrane. Placement of the fuel cell on the vehicle can be seen in the picture to side. Electricity generates in the fuel cell with the hydrogen coming from the fuel tank. This electricity can be supplied to battery and or directly to the electric motor. We look at the operation of the fuel cell. While electricity is produced in a PEM fuel cell, electrochemical oxidation occurs. This chemical reaction consists of the two stages. An oxidation reaction occurs at the anode and a reduction reaction at the cathode. The hydrogen reaching the catalyst layer is supplied to into electron. The membrane in the PEM fuel cell is electron permeable but proton impermeable. Proton exchange passes through the membrane as the hydrogen and reaches the cathode plate. This separate electron charge reach the cathode. The oxygen molecules taken from air entering the cathode catalysis are supplied to into atoms. Two hydrogen protons on the cathode side of the fuel cell to returning electron from the external circuit and an oxygen atom enter the reduction reaction and produce only water as a waste product. The PEM fuel cell model in the simulation program is shown in figure. The actual cell potential, over potential, ohmic over potential, and diffusion over potential and Nernst equation in the simulation so far are present. Okay. PEM fuel cell electric vehicle model image. The driving cycle federal test producer, a new European driving cycle, and worldwide harmonized light vehicle test cycles were selected to compare the hydrogen fuel cell electric vehicle in terms of energy consumption, battery performance, and fuel cell performance in different driving cycles. Results. Operation electric vehicle in conventional driving cycle is operated to determine the performance characteristics of the battery and fuel cell battery power. Fuel cell power and electric motor power change our PFTF75, NDC, and WLTC class 3 driving cycles are given figures 8, 10, 11. Figure 9. Thanks to continuous hydrogen reaction, the PEM fuel cell generated continuous power in the 3 driving cycles. With the electric generated by the fuel cell, both the battery was charged and the electric motor was fed. Charge and discharge conditions can be seen in the battery power change curves in the figures. The points when the battery power curve is below 0 indicate the station when the battery is fully charged. The change of the battery voltage and the current according to the driving cycle is shown in figure. Fuel cell power varied in all driving cycles depending on the demand power of the vehicle. Fuel cell power has always been greater than 0 as the fuel cell conducts electricity directly to the electric motor and battery. The fuel cell provides significant power in sudden acceleration increase, depending on the characteristics of the driving cycle and the maximum speed reached by the vehicle. The power generation amount of the fuel cell has changed. Also, the fuel cell effectively generated power during the cold and high speed conditions of driving cycles.
Dr. Gürbüz, you have 3 minutes.
Okay. The change in amount of the hydrogen used by the PEM fuel cell during its driving cycles and the total amount of liquid hydrogen are shown in figure. The fuel cell operating temperature is shown in figure. The fuel cell temperature change of the driving cycles was determined at the 71 degrees Celsius on the average, according to voltage deriving from the fuel cell. The figure describes the change in the fuel cell power when electric vehicle is the acceleration from to 0 kilometer to 100 kilometers as the vehicle speed increases. The fuel cell power gradually increased with slight fluctuation. When the vehicle speed was constant, the fuel cell power was balanced. When it dropped, it decreases similarly. If motor continues to run even when the vehicle speed is 0, the fuel cell continued to produce power evenly. Fuel cell power did not fluctuate when the vehicle acceleration to high speed. This indicates that the fuel cell is suitable for operation under high load conditions. When the vehicle started to acceleration, first the lithium battery power increased and then the power of the fuel cell increased. The reason for this situation was caused by a short delay of the fuel cell, as seen the example market with the rings in figure. Conclusion. These statistics, as a result of the review, the three driving cycles used can be used to study energy consumption, battery, and fuel cell performance for electric vehicles. The fuel cell responds more slowly to the sudden acceleration of the electric vehicle than the battery. The fuel cell capacity can be increased by the increasing the number of the fuel cell and the anode reaction. With the PEM fuel cell coating method, the fuel cell cost should be reduced by the developing catalyst. Okay, thank you for listening.
Okay, thank you, Dr. Gürbüz. Any question? Okay, I can't see in chat any question. Okay, thank you again.
Thank you.
And now our first speaker, Münevver Tuna Genç, the presentation, her presentation title is The Photocatalytic Hydrogen Evaluation from Green Synthesized Carbon Quantum Dot Structure from Aloe Vera. Okay, are you ready, Münevver Tuna Genç?
I am here. I share my presentation.
Okay. Please share.
Sorry, I can't share.
You can use the share screen button at.
Okay.
Okay. At the bottom.
Oh, sorry, bir dakika. It's okay?
Yes, okay.
Yes. Can I start?
Yes, if you are ready, you can start.
Yes. Hi everyone, I am Münevver Tuna Genç. I get a bachelor degree from the Middle East Technical University. I get master science degree from Selçuk University on the Department of Biotechnology. I am now PhD student at Selçuk University of Department of Biotechnology. Today I will explore the photocatalytic hydrogen evolution from green synthesized carbon quantum dot structure from aloe vera. With the increasing world population, the need for energy has increased, and it has been necessary to find new energy sources because energy resources are insufficient. At this point, hydrogen energy comes to the fore. In the presentation, I will explain to you properties of carbon quantum dots, materials and methods of carbon quantum dot synthesis, and finally, morphological, structural, and optical characterization of obtained carbon quantum dots. In this image, you can see the development stage of carbon nanoparticles. The first carbon dots were discovered in 2004. Due to its properties, it has been used primarily in many areas since its discovery. If we look at the properties of carbon quantum dots, they have carbonic core and amorphous crystalline fragment surface. They have hydroxyl and carboxyl groups on the surface. They can absorb solar energy efficiently. They can disperse in water. They have high quantum yield. It has few sp2 hybridization, so it shows low crystallinity. Thanks to the sp2 hybridization, NPP energy transition take place in the carbon's nuclei. Another, perhaps most important feature is adjustable absorption and emission spectra. It shows fluorescence in different colors as a result of adjustable absorption and emission depending on the change in size. In the image, you can see that the emission shift from blue to red as its size increases. If the FDR analysis, some specific location shows specific bonds, for example, carbon-carbon, carbon-oxygen, etc. These specific stretching vibration at the points prove the existence of carboxylic groups. Moreover, XRD analysis, it exhibits a characteristic diffraction peak between 20 degree and 25 in the 2 theta range. And also they shows absorption between 260 nanometer and 320 nanometer in the ultraviolet region. With the surface modification made, it can be shifted between 350 nanometer and 550 nanometers. And also its absorption between 230 nanometer and 270 nanometer attributed to the PB energy transition of the carbon-carbon bonds, and its absorption between 300 and 330 nanometer is attributed to the MP energy transition of carbon-oxygen bonds. Carbon quantum dots are used in many fields, for example, medicine, biological imaging and detection, green energy studies, solar energy applications, fuel cell applications, electronics, LED lightings, and photocatalytic hydrogen evolution reactions. Photocatalytic hydrogen evolution reactions is similar to the photosynthesis, so it's called artificial photosynthesis. Carbon quantum dots can be obtained from many synthetic or natural materials, but the advantages of obtaining it from plants are more advantageous. These are low cost, easily and quickly available, environmental friendly. Obtained carbon quantum dots have more carbon and oxygen content thanks to their protein, starch, vitamin, and lipid content of plants. And also, depending on the plant's content, surface passivation may occur spontaneously. If we look at the synthesis of carbon quantum dots in the material and methods part, 1 gram of dry plant and 50 milliliter of deionized water were added in the volumetric flask, and that prepared solution was exposed in microwave irradiation at 10 minutes. Obtained brown solution was filtrated and vacuum freeze dried with lyophilizator. In the carbon quantum dot titanium dioxide photocatalyst synthesis, obtained carbon quantum dot solution homogenized for 4 hours after filtration procedure. Homogenized solution was warmed at 160 centigrade degree for 4 hours in the Teflon lined autoclave. After the natural cooling, obtained carbon quantum dot titanium dioxide composite was washed with deionized water 3 times, and dried photocatalyst is obtained. Photocatalytic hydrogen evolution reactions was measured with this system. The sample, which is taken with a syringe from the reaction cell standing in front of the light power, is injected into the gas chromatography device visible on the right, and the measurement is made. In the result and discussion section, the obtained photocatalysts were examined structurally, optically, and morphologically. According to the term result analysis, carbon quantum dots, which were spherical shape, was changed between 10 nanometer to 20 nanometer. You can see picture A. And also you can see easily graphitic-like structure of carbon quantum dots in the HR10 images. You can also see the lattice fringe of carbon quantum dots, which indicate the crystalline structure of carbon quantum dots. You can see the figure B. In the figure C and D, you can see the carbon quantum dot titanium dioxide structure. The distribution of carbon quantum dot and titanium dioxide is homogeneous. In the SEM-ADX analysis results, the SEM images show bulk distribution of carbon quantum dots. The formation of this structure in the form of bulk is thought to be due to the fact that the aloe vera plant has a gel-like structure. According to the XRD result, carbon quantum dots were shown graphitic crystallinity around 2 theta equal to 28 degree. Moreover, XRD pattern of the bare titanium dioxide were illustrated above. The XRD appearance of plain titanium dioxide and the XRD appearance of photocatalyst are similar. In the XRD pattern of carbon quantum dot titanium dioxide composite were shown characteristic peak of anatase form of bare titanium dioxide at 2 theta equal to 25, 37, 38, etc. Moreover, the characteristic rutile form peaks of bare titanium dioxide were shown in 2 theta equal to 28, 36, 55 volumes of carbon quantum dot titanium dioxide composite. In the XPS analysis, the full scale of XPS spectrum of carbon quantum dots was indicate the existence of carbon, oxygen, nitrogen, boron, silicium, silicon, ve sodium elements. You can see these elements in figure A. The existence of trace amount of boron, silicon, and sodium elements may come from the aloe vera plant leaves and do not have any effect on the photocatalytic hydrogen evolution production reactions. You can also see specific bonds of specific areas in the figure B, C, and D. For example, you can see the bonds of carbon in figure B. In figure C, you can see the bonds of oxygen. You can see the bonds of nitrogen in the figure D. In the carbon quantum dot titanium dioxide XPS spectrum analysis shows the existence of oxygen, carbon, and titanium. You can also see the specific bonds of the specific areas in the figure B, C, and D. In the FTR analysis, carbon quantum dots show carbon-carbon, carbon-nitrogen, and carbon-oxygen strategic vibration around 900 and 1600 transmittance values. Moreover, the transmittance value bonds of carbon quantum dots 2750 and 3000 were assigned carbon, hydrogen, and carbon-carbon, carbon-oxygen stretching vibration. And the transmittance bond between 300 and 304 was assigned to the stretching vibration of carbon-oxygen bonds. According to the UV visible absorption result of carbon quantum dots made the highest absorption peak at 250 nanometer and 360 nanometers, and these peaks correlated with PP and MP transition energy level respectively. Corresponding, considering the results of UV visible absorption spectrum analysis and distribution of the absorption range, obtained is similar to the previous carbon quantum dot studies and in coherence with the general optical properties of carbon quantum dots. The maximum emission peak of carbon quantum dots measured at 420 nanometer excitation value. Thanks to the excitation-dependent fluorescence of carbon quantum dots, obtained carbon quantum dots wavelengths shift from blue to yellow. According to the photocatalytic hydrogen evolution reaction, the amount of hydrogen produced by carbon quantum dot titanium dioxide and carbon quantum dot titanium dioxide platin photocatalyst after 1 hour of reaction was measured as 718 micromole and 1224 micromole respectively. After 8 hours of reaction, the amount of hydrogen produced by carbon quantum dot titanium dioxide and carbon quantum dot titanium dioxide platin photocatalyst was measured as 4,513 and 7,918 micromole respectively. According to the results, the amount of hydrogen produced by the carbon quantum dot titanium dioxide and carbon quantum dot titanium dioxide platin photocatalyst showed a linear increase over the 8 hours. Platin, which is used as a co-catalyst to increase the hydrogen production efficiency in the photocatalytic hydrogen evolution reactions. In this study, when the result of carbon quantum dots obtained from by green synthesis from aloe vera using the microwave techniques were examined, it is thought to be carbon quantum dots and synthesis technique will be preferred more in the photocatalytic hydrogen evolution reaction studies due to the environmental friendly, time saving and high efficiency. In addition, it is thought that the efficiency of photocatalytic hydrogen production reactions can be increased by using of different photocatalysts together with carbon quantum dots. It's over. Thank you for your listening. Do you have any questions?
Thank you for your presentation. Dear participant, do you have any question? You can write in chat. Okay, thank you again.
Thank you. Have a nice day.
And this session, the last presentation, Yeşim Molkoç. The presentation title is the study on the comprehensive band alignment of heterostructure. Dr. Yeşim. Okay.
Hello everybody.
Hello.
First, thank you for giving this opportunity to me talking here. And today I will talk about study on comprehensive bond alignment of heterostructures, 2D heterostructures. And I am attendant from the Department of Physics Engineering, Faculty of Engineering, Ankara University. So let me see. Firstly, I will talk about my motivation, our group motivation, and then I will talk about scope of study, results, and then I will deeply stress about the variation of band alignments and optical properties, and then I will talk about electric field effects, strain effect, and I will sum up. So let me continue with my motivation. 2D materials have much interest due to their extraordinary optoelectronic properties in such as these optoelectronic devices. For example, 2D phosphorine and stannine or selenite heterobilayers can be used to understand the tunnel field effect transistors. And another example, one from the 2D materials, hexagonal boron and nitride. This group 3,5 compound is semiconductor with high thermal and chemical stability. However, its band gap is as big as about 6 eV. So molybdenum disulfide also is using for experimentally very useful. So has been demonstrated as a pioneering material because of the band gap device, because of the moderate band gap, because this material has a moderate band gap. And so monolayer boron phosphide, which is impacting here. So monolayer boron phosphide, which has direct band gap and can be used for electronic devices in nanoscale semiconductors. And let me talk about a little bit why it's much interest on all material fields area. And I want to talk about our examination of novel 2D materials because the van der Waals interactions of water bilayers based on these 2D materials have also been studying theoretically and experimentally in all over the world. So in general, van der Waals bilayers, which are obtained by vertically stacking or 2D materials or lateral studying, and why we search more interesting 2D materials, why we get heterostructures, why we need this, because due to the breaking limitation of single 2D materials in the applications of devices exhibit different functional properties than their components. So our motivation for this conference also, 2D layered heterostructures has many good energy storage properties and also energy conversions. So let me talk about our scope of study, what we did. We firstly decided our structures, and then we calculated, of course, some theoretical calculations it was. Strain and electric field effects are considered on the electronic and optical properties. So two different layered van der Waals bilayers is considered here. We are particularly interested in the layer-dependent projected electronic band structures because we need to get the band alignments, an application of the band engineering. So let me go with our method, which method we use. The FTD2 method we use because we have van der Waals structures and then we use this method. We prefer this one. And we use screen hybrid functional was applied to underestimate the band gap values. So we need to check the dynamic stability because of the determination to the structures and phonopy codes we use. So the electric functions of the bilayers to give the information about the optical properties, we have chosen the random phase approximation. And then I will talk about my results firstly. After my motivation, what we did. Okay, let's then continue from here. In here, we have 6 structures, AA1, AA2, AB1, until AB4. So firstly, we think about that. We can put a monolayer boron phosphide layer up to the molybdenum sulfur selenide because it's the Janus structure. And its physical properties will be changed if we change the direction, and our motivation was if we change the layers, what will be the factor of the strain and electric field. And then we have decided which we ask this, which structure is stable, because we have many stacking patterns, and we calculate so we investigated the binding energies. And binding energies can calculate using this formula, the total energy and minus monolayer boron phosphide energy and minus the Janus one. It's the Janus material. And so in here, this table shows us the binding energies of these systems. And if you see the AA2, it is the stable one for both heterobilayers. And this is a stability of heterostructures. I will continue with that because we have decided, okay, AA2 is good enough energy for stability. And then we continue to our calculations for band alignments. And also in here, interlayer distances is also important. We check all interlayer distances, but we have a limited time and I can't show all my figures what we calculated. After this decision to use these AA2 structure, we have calculated the band structures and the phonon spectrum to check the stability. This is our phonon spectrum of this is the second one heterobilayer. We have considered 2 heterobilayer are stable in AA2 phase, okay? And after to consider 2 dynamical stability, what we did, we have examined the phonospectra and the phonobands of both heterobilayers, that the selected structures are vibrationally stable with optimized lattice values are positive as depicted in this figure. And so after that, we also think about interlayer distance. And for interlayer distance are determined, which is good for us. And then after this decision, we continue our calculations, because in my presentation, I will give the red one and blue one graphs. The red ones represents the MBP MOSSE, and the other one, MOSSE, will be an upsides, okay? The colors are important when I present it. So now here, I showed here the electronic band structures of these heterobilayers has a direct semiconducting behavior for that one. But in this one, if you see, it's a slightly indirect. In this figure, the inserted figure, it's a Mexican head-like valence band structure due to the band degeneracy. Did you see here? There is the degeneracy. And actually, we can say first time when we see this image, oh, okay, this graph is so good because it's a direct semiconducting, but we came closely, and it's like Mexican head, like indirect semiconducting structure here. It's so important because the valence band structure due to the band degeneracy at the valence band maximum. So if you see my electronic band structures here, as I told you, there is a Mexican head-like structure here. So why I explained a slightly indirect semiconducting PB. But in HSE, of course, it's in direct properties, it presents. So I showed you the heterobilayers, right? And now I'll check, okay, the chat, okay. And for what about monolayer boron phosphide or monolayer MOSSE? If I see these pristine structures for these have direct semiconductors with these gaps, respectively. So now I will talk about the band alignments. What about band alignments and why we need this? Because if we had the band alignments, we can decide the Schottky diodes, how can we use it, okay? In solar cells, in what are the applications of these structures? So to decide this, we did the band alignments, okay? And I wanted to explain this. We have classically we have three types of heterostructures. I get from this picture, from this reference, thank you, because it explains very good. The type 1, it looks like that, illustration type 1, laser utilizing type. And type 2, it's interlayer extends for D, okay? For example, for the type 3, it's the junction, it would be with tunneling field effect. So what we observed in our calculations, if you see our electronic properties and with using the work functions and band alignments, if you compare it, the band alignments are set as the energy of the stable electron within the vacuum level. The work function of structure is considered by the following formula in here, because it's the work function. And in here, I also showed for each heterobilayer system, the work functions of freestanding monolayer boron phosphide and monolayer Janus MOSSE, molybden selenide. So are found to be this here. I wrote here 5.521 and 4.943 EV. So the band alignments of these kind of van der Waals heterobilayers are determined by layer contribution of conduction and valence bands. In this case, for the leads to a type 1 band alignment at the interface. On the other hand, for the MOSSE/MBP heterobilayer, the contribution to the conduction and valence band is yielded monolayer boron phosphide and MOSSE, respectively, which leads to type 2 bond alignment at the interface of heterobilayer. So the vacuum energy, I think everybody knows, is a special case of 0-point energy. So the electronic properties, how about the charge density differences? It's also good results for this, because the blue ones and yellow ones color represent the charge depletion and recognition regions. By the way, it's clear that the charge transfers from MBP to MOSSE layer, and higher charge transfer belongs to MBP MOSSE heterobilayer, which is compatible with lower interlayer distance and lower binding energy. Furthermore, we have examined the electronic potentials. So
you have 2 minutes. You have 2 minutes.
Okay. I completely finish. And MBP has a deeper potential than MOSSE. So these are all combined with this study, because when we investigate the orbital projected electronic band structures or electric field effect and dipole moments, the band gap charge transfers, it's all combined and continue. If I continue this, sorry. Okay, in here, the electronic band structures and band gap variations of both heterobilayers under the influence of the electric field are presented figures. This shows also type 1 and type 2 band alignments due to the lower CBM and VBM of MOSSE than MBP. It's completely good results, because when we apply the strain effect, we show these figures when we have also biaxial strain and out of plane strain applied, and then we get many band structures, but it's closer. So let me talk about the types, and types change, but in here there is an effect for external electric field. If we have an electric field like that, minus 0.1 voltage divided by angstrom, and we have type 1 and type 2. So let me look the optical properties. Frequency dependent imaginary dielectric function is also good, but it gives us the blue. We have a blue region, violet, and we have UV region, visible UV and visible regions. So we can just say as a summary, we can present this representation, propose a solar cell to describe the intrinsic electric fields. And the last one, the last slides, this, because we have also proposed schematically proposed experimental procedure, up, down, bottom and top experimental procedure, preserving the band alignments under the influence of the external electric field and strain, provides freedom in the design of optoelectronic devices. Thank you for listening to me. And also I want to thank my university to support us and also to be tech for resources. Thank you so much.
Thank you, Dr. Molkoç. You have a question. I read from chat. The Fatih Erşan says, did you check your CBM and VBM energy levels for the heterostructure? They can be suitable for water splitting process.
Actually, we have no time to check them, but we can check and then we can do that. It's really good idea. Thank you, Fatih. Thank you, Fatih Erşan. We will check.
Thank you. Any question to Dr. Molkoç? Okay, we don't have any question. Okay, now we are at the end of this session, and I close the session. Thank you for your participation, and the new session will begin 2:30. Okay.
Thank you. Bye.
Thank you. Bye.